Starting short review of Latimer and Porbaix diagram. It's easier to interpret data when they are displayed in visual form of diagram, for example. Standard reduction potential for related set of species can be displayed as reduction potential diagram, which is sometimes called the Latimer diagram. There is a famous reference book of Latimer. Latimer diagrams display redox information about series of oxidation states in very compact form. Let's look at such diagram of oxygen in acidic solution. You have O2 that can be reduced to hydrogen peroxide with potential 0.68 volts positive, which in turn can go to water with potential 178 positive. So oxidation numbers are 0, -1, and -2. Oxygen doesn't have positive oxidation numbers. And also you can go directly from O2 to H2O with a redox potential 123. Now you need to add hydrogens to balance the equation, but that's kind of automatical. When you making water from H2O, you need 2 extra H pluses and of course 2 electrons, counting oxidation numbers. When you go from O2 to H2O2, of course you need 2 hydrogen ions and 2 electrons. And when you are going from oxygen to 2 water molecules, you need 4 protons and 4 electrons. So you can easily balance these. If you want to reverse the reaction, you of course reverse the potential, but this is not a standard potential anymore. From this diagram, you can establish that hydrogen peroxide is not thermodynamically stable. Another interesting example is diagram for iron in acidic and in basic solutions. So the highest oxidation number of iron possible is 6, and you have ferrate ion, which is actually unstable and with redox potential 2.2 volts, very high, goes to Fe3+, which in turn come into Fe2+, 0.77 volts, it's not too high, and negative potential 0.44 volts to iron metal. You can jump from Fe3+ directly to iron metal with potential close to 0. As before, you need to write a balanced equation, which again is possible if you just count how many oxygens you need to place as water and how many hydrogen ions you need to make that many water molecules. And of course, number of electrons is coming as a difference between 6 and 3 electrons. In basic solution, it's much different. You have still oxidation reaction, Fe or 4 2- still strong oxidizer, but much weaker than it was. Fe3 plus is no more oxidizer. Actually, it will be FeOH2 going to FeOH3. And this number is far more negative. So everything is coming to more negative numbers. It's very helpful because you can write all these numbers as a scheme and then just play with them mostly without any calculations. Porbaix diagram helps us to see what's going on at different pH. So at y-axis you have potential, at x-axis you have pH value from 0 to 14 usually. So in between you have predominant species. For example, for water, this gray area is area of stability of water H. If you have oxidizer stronger than this, water will go into oxygen and make H+. If you have reducing agent stronger than this potential, hydrogen from water will react with electrons to make hydrogen gas. Of course, you understand that at pH 0, water is not water, but 1 molar solution of some acid. And at pH 14 is not water again, but it's 1 molar solution of some strong base, say sodium hydroxide. A similar diagram is for Fe3+. You can see that ferrate ion at pH 0, so acidic, has a redox potential 2.2, remember from Latimer diagram. Then at 0.77 there is area between Fe3+, so this is area of Fe3+ dominance, to Fe2+. Below 0.4, iron should be solid metal. What about pH? At pH approximately 4, iron will precipitate as iron hydroxide, Fe2 or 3 with hydration water. At pH around 8 something, you have Fe2 plus coming into iron hydroxide, FeOH2. There is also mixed oxide, Fe3O4 here. So you can see at which pHs and redox potentials each of these forms will be thermodynamically stable. So in acidic solutions you have 3 plus ions, 2 plus ions, and at basic solutions you do not have iron ions at all, you have different hydroxides and ions containing oxygen. It's very helpful diagram. I will be using it once in a while.